Welcome you all for a UGC program on laser physics under Swayam platform. Now, consider this particular equation. You are all very familiar with this one. This is the very famous, just as I would say, it is a Nobel Prize winning equation, energy density, Planck's law of energy density in a black body radiation. Now, rho represents the energy, nu represents the frequency range, rho d nu represent is equal to 8 pi h nu cube. Nu is the frequency of the radiation, c is the velocity of or a speed of light, the rest is you know, divided the d nu divided by exponential delta E divided by k b t minus 1. This is a very standard equation with which you all must be very familiar in your undergraduate. This is black body radiation equation. We are going to take this equation and try to find a way how you can devise a certain kind of instrument where you can make stimulated emission bigger than the spontaneous emission, so that you can get a coherent laser radiation coming out. That is all. Now, coming back to this one, the above equation represents the number of quanta, number of photons per unit volume in the above frequency interval. This quantity out of this one, 8 pi nu square divided by c cube is a very well known mode density. What is the mode? Mode is the, if you take ordinary string, if we have one another node, if you just pluck it, you will have one half wave standing wave. If you pluck it somewhere here, you will have one half another like this one. So, you will have one half wave. If you pluck it elsewhere, you can have two half wave. If you pluck it somewhere else, you will have three half wave. Each half wave represents a particular mode, a particular frequency. That is the reason why in any violin or any stringed instrument, choose this point or push another and choose here, each one will produce different frequency. What is important is you can produce so many frequencies in a certain volume in a container. Imagine that you have got a container of 1 centimeter by 1 centimeter by 1 centimeter. This will represent a typical energy density, and also what I have given now, 8 pi nu square over c cube represents the mode density, the number of modes that are possible to be produced inside. Now, if you compare the equation, this equation and this equation, put them together, automatically you will come to one simple conclusion. This particular quantity exponential delta E over k subscript b, k is a Boltzmann constant, T is a temperature, and minus 1, inverse of this one should naturally represents the number of photons per mode, is something called photon occupation number. That means, what I am trying to say, you have so many modes, how many number of photons can be put in particular mode, that is what you mean by photon occupation number. Imagine if you go to the hospital, take for an hospital, if you go to hospital, you will say in this particular cabin there are 20 beds, which means there are only 20 people can be accommodated. In a similar fashion, we are going to say how many number of photons can be put in each mode, that is called the photon occupation number. Now, put all this one, insert whatever I said in this equation, immediately you can see B rho, the stimulated emission rate, divided by spontaneous emission rate is equal to the photon occupation number. You need to do some time and put this equation and check all this one, which I cannot do now, it is not in the board. You must take it as an exercise. From all the equations that I have given, you can arrive at this equation 3. Now, it means under thermal equilibrium condition, in the visible region, the mode density is so high that NP is less than 1. Okay, so what do you do now? Then how to have a laser? How to get a stimulated emission greater than the spontaneous emission? The above equation immediately gives you the clue. First thing, forget about the black body radiation, which I considered earlier when I said take a box of 1 centimeter by 1 centimeter by 1 centimeter, and this is closed. We call it a black body radiation because you will have some radiation inside. That kind of container will not be useful for our laser process. So, forget that one, throw away that one. All what you should do is take a new type of container, which is called a cavity or a resonator, where only few selected modes are allowed to exist, and first carefully suppress all other modes except few selected modes using a linear resonator. That is the first point. This is something equivalent to saying, coming back to the soldiers, when Indian Army wants 1000 people or 10,000 people this year, make announcement that any able bodied person in the age group above 18 to 25 is welcome for Indian Army. Then many people will go out of, then they will ask all the people, just go for running, run for 2 kilometers. By the time they run out 2 kilometers, most of them will feel sick. So, 20%, 30% of them will be out of selection. So, first filtering done. Then second, they will select, they will ask all the people to jump so much distance. In the jumping race, another 20% will go. Like that, they will keep on eliminating people one after another. Eventually, they will try to get the best able bodied men who are ready to take the strenuous exercise. That first selection itself is very important. Only they are recruited and taken for further training. In a similar fashion, first thing, you must have a laser resonator. Look at the laser resonator here. I take a long tube, let me say for a helium neon laser, maybe many of you may have seen it. A helium neon laser will have this kind of length, about 1 meter length, and the diameter will be 2 or 3 millimeter diameter. In that, I will take helium and neon gas at a pressure of about 20 to 30 millitorr. Extremely small pure helium neon gas will be kept inside. That means, I have first taken one selection. Secondly, I will have one end a positive, other end will be negative, produce a discharge. That is the first step. Whenever there is a discharge like this, electron from one end, from negative, run towards the positive end, it will keep on running there. When it runs, it will come across helium atom and neon atom. It will hit helium atom and neon atom accidentally, not willingly, because it is never interested in hitting helium or neon. It wants to go to the positive anode. On the way it comes across, hits a helium and neon. When it hits helium and neon, helium gas gets excited, neon gas also get excited. That is the first step. But remember, all the excitation takes place in this side. Some excitation will take place a little this side, that is all forgotten, but the most of the essential excitation will be in a linear direction like this. Then what happens? You put one mirror on this side, this is what I have said M2, and there is another one M1, there is a mistake, it should be M1. There are two mirrors, this side and this side. These are the two mirrors put together called a resonator cavity, a resonator. Next step, in fact, the step which I forgot to mention is the pump in the diagram. the pump is the electrical discharge, which need not be shown here, but schematically I already have shown this one. I produce the electrical discharge in a gas tube of 1 meter length and about 3 or 4 millimeter diameter. By this process, I have chosen the light going back and forth only in this direction, not in this direction, not in this direction. That is the first step. Next step, I put 2 mirrors here. Then what would happen? The light that is going this way, most of the time it will go back and forth. That is the second step. Third step, look at this diagram. Some of the photons which are emitted by spontaneous emission, some of the photons which are emitted by spontaneous emission along positive x direction, look at this, there are 2 photons which are moving in this direction. They will produce stimulated emission along the positive x direction, because these 2 are traveling in this direction. 2 spontaneous photons produce stimulated emission. So, now we have got 4 stimulated photons moving in this direction. Then what I do? I have a mirror M2, these photons go and get reflected. M2 has a reflectivity of 100%, which means whatever light falls on this will be reflected back. Then this photons will go back into the medium, back into the discharge tube. Remember, all the time the discharge is going on, like a tube light, the discharge is going in the helium neon gas tube light, then the light goes back. During this process, these photons, 4 stimulated photons, will stimulate further photons. They will interact with the excited atoms and stimulate further, and by the time they come to the left side mirror, they would have grown into 400 stimulated photons. Here again they are allowed to go back. Now, 400 stimulated photons going back again into the medium where there is a population inversion, they will produce 4000. When they come out into this one, by the time there will be 40,000. Now, they will go back and forth many times. Why many times? Look at this one. The length is about 1 meter. The time taken for 1 meter for light to go is about 3 nanoseconds. Whereas, when I excite helium neon gas and if I excite it strongly, you will have population inversion existing for about 3 microseconds. Now, look at it, 3 microseconds, up to that these atoms will be waiting, they will not produce spontaneous emission, they will be waiting for 3 microseconds, but the photons go back and forth every 3 nanoseconds. That means, the photons, stimulated photons, have 1000 chances, 1000 times to compel the excited atoms to produce light in their direction. That means, I take ordinary people, train them 3000 times, and then I turn them out as soldiers. In a similar fashion, the spontaneous photon going back and forth few thousand times will compel, force most of the atoms to produce light in the same frequency, same direction, in same phase. Then you will get light from the mirror out, from M2, which is called the output mirror. There will be a small hole through which light will come out. That is the laser radiation which you can see in any laser of helium neon laser. What is important at this point is only this: any laser has a 3 component. First thing, the active medium may be a gas or a liquid or a solid. Good example for gas is a helium neon, argon ion. These are 2 very popular gas laser media. For liquid, you can have a dye solution. Some of you are fluorescent dye solution, or rhodamine dye solution. These are all very common cheap liquid media. Or you can have solid media like a neodymium YAG crystal, which is a hard crystal. Ruby is another crystal. All these are solid insulator crystals. Or you can have a semiconductor material. Any one of these material is okay, corresponding to the kind of material you have chosen to produce laser. You must plan for a proper pump source. The pump is the one which produce or which supplies energy to produce population inversion. Without population inversion, no laser. Without pump, no population inversion. So, you must give external energy either in terms of electrical discharge or optical pumping, optical shining, or current injection. You can inject lot of electron inside. In fact, in a semiconductor laser which you have seen earlier, all that we do, we have a battery, electron in the battery will pass through, kick the electron and hole to come together. The electron in somewhere will be forced to fall into the trap, and then they will produce something called exciton radiation. If the exciton radiation is properly organized, you will get a laser from semiconductor. If the exciton radiation is weak, if it is not sufficient to come out under population inversion condition, you will get LED. LED is a light from a diode, but it is not a laser. LED is incoherent light. The same LED, if you can properly design, it can become a laser diode, it can produce a laser. The difference comes only in the design, but this took a lot of time. Now, what I am trying to emphasize is, you must have seen many gas tubes, color tubes, red, pink tubes in the advertisement, yellow tubes, orange tubes. All these are gas discharges. Maybe it is a helium or a neon or argon. These are all used for advertisement. We take one such gas like a helium and neon put together in a specially designed tube which is 1 meter long, 2 millimeter, 3 millimeter diameter, pure, very pure form, produce electrical discharge very much like what you see in the any market, same kind of electrical discharge. Only thing is, it will be very strong electrical discharge. The additional one which you do not have any other advertisement lamp is a 2 resonator mirror. Once you have these 2 resonator mirrors, these are the 2 mirrors which will produce specific feedback, which will send back the light, go back and forth, produce more and more trained soldiers, produce more and more coherent light. Until then, it will not allow them come back. Once all these things are carefully designed, you will have a laser. In this case, I have explained with the reference to helium ion laser. The same story holds good for neodymium YAG laser or a carbon dioxide laser. All of them are based on these 3 essential components. First one, active medium. Active medium means it should be capable of producing light. The light that it produces will be first spontaneous emission. It is a spontaneous emission which acts as the seed to produce stimulated emission. Many people miss this point. It is a spontaneous emission which acts as a seed for stimulated emission. Again, the best example I can say, all the trained soldiers that we see in the Republic Day parade are not people from alien country. They are not people from Mars or from alien. They are all people like you and me. They are all common people, but they had been trained. They had been carefully recruited, carefully trained over and over. So, they become orderly, trained, disciplined soldiers. That means, it is a spontaneous emission which acts as a source for stimulated emission and laser action. One more important point is you can have continuous wave laser, which means once you switch on, the laser will keep on coming without any stop. This is what you had seen in some of those demonstration earlier. All these are diode lasers, CW or continuous wave lasers. This is one example. There are another type of laser which is called pulse laser, which comes as a pulse by pulse, shot by shot, like a stream of bullet. You must have heard about AK-47. What do you mean by AK-47? Once it starts, it gets stream of bullets, but remember, between one bullet and another bullet there is always a time gap. In a similar fashion, we have another type of laser which is called pulse laser. The most common pulse laser which is available in the market and which is very common in many hospitals is a neodymium YAG laser. It gives pulses after pulse. The pulse duration is about only 10 nanosecond, but the time between two pulses will be 10 second. You see, 10 second is billion times longer than 10 nanosecond. It come one wait long time and then it another comes. The pulse width is very small. The lasers exist only for a short time, but another pulse comes after 1 second duration. This is the type of pulse laser. Now, in the earliest stage, at the beginning, we had usually millisecond laser pulses, then we had microsecond laser pulses, after some time we had nanosecond laser pulses, then we had from nanosecond we went on to picosecond laser pulses. The pulse width is about 10⁻⁻12 second. Then I have worked with the femtosecond laser pulses with the 10⁻⁻15 second. Now, interesting thing is when I finished that one, it is about 15 femtosecond is the record which we did long ago. Now, this year Nobel Prize was given to few people who have got attosecond laser, where they had produced laser pulses of 10⁻⁻18 second. It is an extremely small event, the smallest event that you can ever see anywhere in any part of the universe. This is something fantastic. It is a monumental achievements of a human endeavor. Thank you very much.